So what's the mean, given the data that you got? What's the mean of x1? Doesn't it say that the mean of x1 is 0 and the mean of x2 is 0? Are x1 and x2 orthogonal? No. x1 and x2 are not orthogonal because their cross products add to 20. From that table, because the means are 0, could I figure out the variance of x1 if I wanted? Sure. Because I know from here that the row 1, column 1 position tells me the sample size. Since I know the mean of x1 and the mean of x2 is 0, if I want to know the variance of x1, I just divide 40 by 32, and I've got the variance of x1, if that was something I wanted to know. If I wanted to know the variance of x2, I could just divide 60 by 32. If I wanted to know the covariance between x1 and x2, I would look at the off diagonal and divide by 32. So there's a lot of information in that matrix of cross products. Is it useful to ask you to have thought this way? Well, hell yeah, it's useful. Because in the bad old days of SAS and SPSS, they would read in your entire data matrix. So if you had a lot of data, they used up huge quantities of memory. Made it impossible to do things that had any size to them. The reason Bill Green became, one of the many reasons, he's a really smart guy, the author of the textbook, and really, really smart guy. One of his claims to fame is authorship of LIMDEC, one of the leading econometric software packages. Well, what's such a big deal about that? Well, the big deal is that the whole, you can use, you can buy the full version of it, you can read in, you can work with data sets of any dimension that you want. Because the software only works with these cross-product matrices. He's only reading an observation on a variable at a time and slowly accumulating the sums and the cross products. And then as he gets finished reading a row of data, he drops it. So once it's finished reading all the data, the only thing left in memory is the matrix of cross products. So instead of, in this simple case, in this simple example, instead of having a matrix in memory that's 33 rows and 3 columns, he's only got a matrix that's 3 by 3 and symmetric besides, so he can drop off n times n minus 1 terms over 2. Because he only needs the top half the matrix and the main diagonal up. Huge savings in computer memory. Which means then that you can, the memory that you don't need, you can use to do calculations in double precision. What's that? You're an engineer. What's double precision? What's the next stuff like this? Again, in the really bad old days, when everybody was running on an IBM mainframe, a word length was 8 bits. So if you wanted double precision, if you wanted to carry some significant figures, you had to use double words, double precision. 8 bits to 16. Nowadays, with 32-bit computers, a character is represented by 32 bits. With double precision, you can carry it out to 64, which means that you can measure a number to extraordinary precision. In order to work with a lot of data and not accumulate the rounding errors, you got to have a lot of memory. You'll have very efficient software. So that was one of Bill Green's big breakthroughs in software programming, which was many 30-some years ago. They wrote the first version of the Internet. He was doing this thing. They're trying to read all the data like SAS, having a working file with all the data in it, and then also going to all the trouble computing all the cross-product matrices. He said, I don't need all that. I don't need to keep track of all that data all the time. Because I don't need to keep track of it, and because I only need half of the cross-product matrix, I can rededicate all that space dynamically to carrying double precision numbers. This was a controversy in economics, by the way, I guess maybe 8 years ago, 9 years ago. There was an article in the Journal of Economic Literature about different competing software packages. And they gave if you do anything with nonlinear regression or simultaneous equations models, any numerical errors or rounding errors are accumulated because of the way in which they're repeatedly passing through the data. Not the way nonlinear regression works is that you do basically you do Taylor series expansion on the function that you're trying to minimize, and you get a set of starting values, you see how far you are from the errors you made, and then you go back and revise the starting values. So you're always accumulating errors as you pass through the data. So if you're only working in single precision numbers, your end result can be quite different from software comparative software. Somebody wrote a paper, including JDL, where they compared SPSS, SAS, which were the two leading software packages in industry and academia, and they stood them up against PSP, LINVEP, and some of the other packages that were written by economists and statisticians. And it turned out that SAS and SPSS really stank, because all the calculations were done in single precision. They were so embarrassed by it that they went back and fixed it. So now it's not a big deal. Okay, so let's continue on. So for you to answer things, the first question was to find the regression coefficients. So we're given x transpose x, we're given x transpose y, and the regression coefficients are given by x transpose x inverse post multiplied by x transpose y. So you had to find the inverse of x transpose x. And of course, the first job is to figure out the determinant. You did that for homework one night. And one of the things that you discovered in that homework assignment that you did was that it always pays to look for the row or the column that has the most zeros in. And so this one was, you couldn't help but pick a row with 2 zeros or a column with 2 zeros. All you had to do is look at the first row or column and expand on that row or column. But sometimes in the heat of the battle, the heat of the exam, one forgets that. Oh no, I guess I didn't forget it. So the determinant of x, expanding on the first row or column is the same, doesn't matter, is just 33 raised to the power minus 1, where minus 1 is squared. And where does the squared come from? Well, it comes from the sum of the row column index. So if the sum of the row column index had been odd, it would be minus 1 to the cube. And why is the minus 1 up there? The minus 1 is supposed to be times 33. I don't know what happened here. Sometimes when things get, I guess, the conversion from MathCAD to RTF moves some things around. So the determinant of x is just 66,000. Okay, it's followed by, right, 66,000. So then you have to find the cofactors. And again, if you had your wits about you, you could sort of use your pencils to see for yourself that really didn't need to do too much work to figure out the matrix cofactors, because anywhere there was a 0 in the matrix you started with, the corresponding, because of the number of zeros and where they fell, you're going to get zeros in the matrix cofactors. But nevertheless, if you were doing all that bookkeeping, I reproduced it here for you, so that the row 0, column 0, using MathCAD's subscripting method, is minus 1 to the second power times the determinant of the matrix that's left when you take out the first row and column, and so on and so forth. And so these two cofactors turn out to be 0. By symmetry argument, these two also are 0. And so you only have to do 4 more numerical calculations. And then x transpose x inverse. So xtx, the lowercase t, is not actually an operator. It's just my notation. And INV, so that I can remember that I was computing the inverse. By definition, the inverse of xtx is 1 over the determinant times the transpose of the matrix of cofactors. Or that would be xtx inverse.